Okay. I can't pull that up, so it'll be a little more of. So this is the big picture we want to do. So we define what we call this random variable, which counts the number of vertices whose connected components are of size at least k. Okay, so there is some confusion about z greater than k and c max. So suppose I give you that is greater than 1. Greater than equal to 1. What relationship exists between c max and z greater than equal to k? Let's do something very simple. Let's make it explicit. Let's not worry about what we showed last time. What kind of sequence is that greater than equal to k? As k increases, what happens to it?
So decrease,
Not increase.
not decrease.
Not increase.
Not increase. Yes.
It's a non-increasing.
Decreasing set of events.
It's not strictly decreasing, so that's why non-increasing.
Yes.
That's so if you notice that, what can you say about the relative side of these two quantities? Can you compare the two? So that one observation that zk in fact is not increasing tells you something about this.
Yes. We are. This is the only thing in the set. Right. If we increase k and zk does not change, it means it is equal to c max.
No, but for a certain number, something is happening. Then what does it mean?
We know that zk is greater than equal to c max.
No, I'm asking you exactly that. What relationship holds between the two quantities? Let's not say what we know. Let's just make it explicit. Is it greater than equal to, less than equal to what?
Greater than.
Greater than equal to. Okay, so let's try to prove this.
No, zk is greater than. Less than.
Okay, let's try to prove this. If zk is 0, then definitely this is not true. Right? Because C max can be non-zero. But when zk is greater than 1, is this true? Is the question. Yes, maybe. As I said, just look at the observation. In that case, decrease. That's it. What does it tell you about this? Try to put the counter positive. Can C max be greater than this? That would prove this. So either we prove that, or we prove this directly. What is the one line argument for that?
So GK contains the largest cluster and all the subsequent smaller clusters.
Correct.
That is why it has to be greater than.
Okay. Can you make it more precise? No, what is not clear?
I'm thinking how to.
Yeah, so what connection can you draw between them? Is it possible that C max is greater than Z? Let's try to think of that. How will it be possible? What has to happen? Go back to the definition, and the fact that
K has to be greater than C.
Sorry?
Then K has to be greater than C max, right? K.
strictly greater. See, this is less than equal to, so equal to is already contained. What's the definition of C max? C max is the largest possible.
Correct.
So suppose it's greater. What does it tell you about this?
This is the right?
Sorry.
GK should be
You're saying if mod C max is greater than Z, then
GK should be good.
why is this true?
So it means I have chosen a key which is greater than the size of the largest cluster.
Okay.
And beyond that, there is no cluster. So, okay. Is it wrong?
No, I'm not saying right or wrong. I'm just this is all there is to it. So if you don't follow this, things will be very difficult going forward.
Yeah.
I thought this was clear, but towards the end I realized that maybe it's not clear. So there is nothing more to be done. This is it. No extra information is needed to conclude that. But I want you to think about it before we go forward. You don't want to look at this, look at that. Okay. Whatever you want to do.
So if C max is greater than Z greater than equals to K, then K should be strictly greater than C max.
What is the relation to K and C? Why?
If not, then like
But what would you gain by connecting C max with K?
because only after crossing that G value G greater than equals to K would be equals to G. Otherwise, it will be containing
So
C max
Okay.
number of
So-
vertices. Because of that, we can conclude that G is greater than equals to K is equals to 0. Because if it is not 0, then there exists at least one vertex which has connected component which has means greater value than C max. And C max will not be giving like something like
The C max is C max plus 1.
something more.
So finish the argument. If supposing there is an argument.
I'm not able to speak it properly or in an organized way, but
So try to prove it directly. You don't necessarily have to prove it.
there we can show it to be true by taking three cases of k. Like when k is less than c max, when k is equals to c max, and when k is greater than c.
Why do you want that ugly business?
Sorry,
Why do you want to get this ugly?
another way.
What is ZK? What is ZK? It's just counting a number of vertices which are components greater than k. Why is that sufficient?
Yes.
So listen, you want to draw a graph. This guy has this. Let me just, so this guy. So these guys are part of. Belongs to that. Now, what does Cmax have to do with this?
As long as zk is not zero, it will be containing c max. Means all the vertices that are associated with c max.
Just think about it. Zk is a decreasing sequence. Cmax better be sitting to the right of this.
Yes.
Just think of it. It's much simpler rather than be doing anything wrong. Okay. So Zk is less than equal to Zk plus 1. So where does Cmax sit in this chain? To the right or to the left? Somewhere to the right,
To the
by
right,
definition.
yeah,
So why isn't that sufficient to prove this? This is true
Yes,
by definition.
yes,
Where does Cmax sit? Somewhere, somewhere it gets equality.
yes.
So what does it mean? Sorry, it's not understand.
It will be.
So somewhere down the line, this is exactly equal to Cmax. That proves it. As I said, just use the fact that ZKs are decreasing.
Okay.
You don't have to do any case, nothing will happen. It's an important observation to make for whatever this is. But this is not true for when it's zero. That's the only case you have to worry.
Okay.
Because Cmax can be larger than zero. All right, so now let's begin. The basic idea of the following. We want to control the Cmax, but instead of Cmax, we control V greater than K for value capital K log n. That's what we're doing now. So what we have done so far is we have defined my side again. What we really want to do is to somehow connect this to capital K. Okay. That's what we are really after. We will also show that there are no. So, the next step. So we'll first look at expected number of that greater than capital K. And we'll show that this is equal to n times. Let's see a show already. By definition. Using K analysis. This was always true, and then we showed that this is some n times. That's what you already understand. This probability is actually computed to be equal to this via the domination. upper hand. So let's call it sign. That's what we did. So we sandwich this process from both above and below by branching, pause on branching process. We have okay parameters. And we'll also show that there will be n minus that key with high probability. We can come into the power new where new will be half an. So that's what we are heading last. So what more do I need to do to get my result ready? I need one more step. That the probability that there is any vertex will be such that the connected component is greater than kn and it's smaller than alpha log n. This there is a vertex for which the connected component is larger than kn but smaller than alpha times log n. And if I can show that this is small, then eventually Pmax is nothing. So then I can really look at capital K log n, which is nothing but little kn. For remember that this is little k. Then these quantities are simply equal. So there is nothing in between. So if I'm looking, so this keeps going down. Cmax, sorry, the Zk is decreasing. Now I tell you that from Z, K log n, the alpha not log n. There's nothing there, empty. So even if I'm counting from here, all I'm counting is things above. I'm counting actually things to the right of this because there's nothing in between. That is why that relationship. Well, this I've done, we do this and this so that we can actually control this. That's the big thing. We don't have direct handle on Pmax. We are doing it via this random variable. We are greater than k. All right. So what the lemma we embarked upon, wanted to move forward. So let me just select it. This chi less than k of lambda. Remember, NLP is the expected value of C of B given C of B. That's just a definition. Given that the connected component size of a particular vertex is less than k, what is its expectation? That's it. Then we want to show variance of b greater than k. That amounts to lambda k. So if I write lambda, so this is the result we wanted to get. So what we did was we got variance particular. I. Yes. They are connected. Plus. Same thing. And you can do this because the LK is nothing but an indicator. That's what essentially is going on. There is nothing really going on until so. Okay, remember what we did? So something special. When I was connected to J and I was not connected to J, something interesting happens. So when I is connected to J, these two are essentially the same. The connected component I is connected component. That is what we actually used last time to write it as a function of I. So that was it last time. I will redo that. This is what we were actually at when they were not connected to each other. What is the interesting property when they're not connected to each other? So essentially separated. Okay. So what should I? If you remember, it's okay. If you don't remember, still you can work this out. How do I typically write a joint probability? I write the joint probability as P of A times P of B given A, P of C given A comma B. The three ones. Yes. 2, 3. And that's what we will do. So, be that. Let's write C of I equal to L. G E and this term will be the wrong one. This will keep as it is. And the last term is what we on the work is going to. Okay, so now tell me what should I do? What this tells me is that I and J are not connected. This guy is connected component of size and what is the probability that the connected component which is less than equal to. That's the probability we have.
The this probability is independent of I.
Independent of I. What does it mean? So there is some I. Whose connected component is FC of I. And size is L. There is J. Whose connected component size is less than J, but I and J are not connected. So that means it is some other thing which has no common edge going through. That's all it is. Because if you have any common edge, then it will connect. What can you say? What is this probability? This is an observation you have to make. And anything on the board to make it observation.
We can take a graph which is of size n minus L.
Okay.
Then we can directly talk about any connected component being less than k.
So what is the final probability minimum, right? So this is the probability. So what is the probability in that new graph?
P of Cj less than k, but the size of the graph will be of n.
Exactly. So essentially you're keeping the L vertices out
Yes.
and redoing the whole process all over.
Yes.
So essentially what has happened is this event only depends on what is happening in the L minus L vertices. This event does not depend on what is happening on the outside. We know that they are not coming. So I might as well have just looked at the smaller graph, which only has L minus L vertices. So this is nothing but the probability of Cj less than k in a graph, understanding graph with L minus L nodes and probability P of connection. Right. This is equal to the probability that is less than k. But now the parameters are N minus K. Okay, I want some further simplification of this quantity. What more can I do? Is there a connection to this probability and the probability that k with n comma p's? Can you connect these two quantities? Only the graph has changed. The event is the same. One is a smaller graph, other is a larger graph. So what do you think? At least you can relate it to. Which is larger? The first one, because the smaller graph, so the better. So at least one property I think that the first is larger than the second. What if I want to take a difference in the two? And for this, think of coupling on this graph. If you look at two independent graphs, one with size n and one with size n minus l, it will be difficult to say. But can you find the coupling where you can actually compare these two graphs? We've done this argument multiple times. It's very difficult to compare two random variables. But there is some coupling in which it becomes very easy to compare certain things. So it's a graph you can think about where you can actually compare it very easily. So if you do an independent copy of n minus l nodes and independent copy of n, very difficult to see the difference. Even I don't know how you prove that one is greater than the other. How did you prove it? Without the coupling, how did you prove that the first one is actually larger than the second?
What?
You said that the first term above
Yes.
with vertex n minus l vertices is larger than with n vertices. Without a coupling, how did you actually say that that is larger? It's intuitive, I agree. When you start proving it, you need a coupling. Just like when you did for binomial, or just for proving that the understanding graph has non-dominant properties. We needed a coupling. So even to say that that probability is larger than this probability, you need a coupling. What would be that obvious coupling?
So this is larger. I thought they are roughly equal.
Why? It can't be equal, right? Otherwise the difference is zero.
No, sorry. The difference between the
Forget the difference. Just look at the first quantity where the probability is being computed with n minus l nodes.
Yes.
And the second where there are n nodes.
yes.
What is the relationship between these two? Which is larger? It appears that the first should be larger than the second because
Yeah.
it's more likely to have a smaller component than the second.
Yes, yes.
But again, how do you actually precisely prove it? You can prove it simply if you give me a coupling. So what is the most natural coupling when looking at the Ardeshani graph with n vertices and with n minus n vertices? This is an obvious one.
So, do you want to consider two graphs with same nodes but different P's? No?
P is same. It's only the number of vertices that change. See, what was the coupling before? We looked at the same two graphs with same number of vertices. We just increase P. So in that case, what did we do? Whenever I put an edge with a smaller P, I always put an edge with a larger P also. Edge by edge, I could match.
We need to consider two graphs then. One of n minus L, one of L.
One of n. So somehow you have to go from n minus L graph with vertices n minus L to graph of n. P remains the same, so there is no P change. Isn't this obvious to you? It is not. To think of this as understanding in the same comma. If I want to go to understanding of n comma p, what is the simplest thing I should do to this graph?
So the connection between.
No, I should introduce first n vertices and allow them to set my L vertices. I should consider R with L comma P. And between any S and P here, allow them to be connected with probability P. This is how you would construct a bigger graph from a smaller graph.
Yes, yes.
If I give you an adversary of this and an adversary of this, how would you make an adversary of n comma p? This is the way to make it. Now can you think of the coupling? What is the right coupling? Originally, what is happening here is there is two independent components. One is understanding of n minus n comma p. Another is understanding of n comma p. I want to go to a coupling where I can compare the two. So that's all I'm interested. When I talk about a single graph in some sense, which are right now they're not comparable. But I want them to be comparable in some way. What is that obvious thing? What is the distribution of this graph so constructed? If I combine them, all the edges, this is understanding of L minus 1. So this is, let's call it ER hat, and the whole thing as ER hat of N comma P. I can do so.
Yes.
Now I'm in the same space where marginally I have the same distribution, but it's the same graph. Now this is very easy to compute, to claim that this is larger than this. So I'm in the same graph. What is the probability that this is smaller than k compared to this smaller than k? On a different graph, it's difficult to compute. Now the same graph, so it better be that if this is true, then this better be true.
Yes.
So one is always larger than k.
Yes.
Now think of the difference of the two. Difference of these two probabilities on this graph, which is common. That's what your doubt initially was. You never made it so far. Now, what you want to compute is probability. You can upper bound is also fine, you can give an equality, that's fine. But the advantage now is that you're on the same ground. So whatever intuition you have is actually the correct intuition. So what interpretation should we have is think of a big graph. First probability is being captured by only looking at the subset of subset. The second is over the whole graph. That's all right. But it's a single graph. So now you can interpret it whatever your interpretation is. So what does the intuition suggest? What should this difference be? So it is subtracting a probability. What is it effectively means? That you're discounting certain events, or you're accounting for the complement event. So what does it mean? That on the smaller graph, mod Cj should be less than k. So on the bigger graph, mod Cj should be greater than equal to k.
Sorry, I didn't.
See, I can only give you an interpretation. When you want to say P of A minus P of B, what is effectively meaning? That A is happening, but B is not happening.
Not necessarily, or necessarily. Why? Not happening, B will be 1 minus.
That is too brutal. I'm not saying it's P or B not.
Here also, if you think of it like that, then that interpretation will mean sum of two probabilities such that the second probability will be greater than k. Something like that.
Look at this big graph. In this big graph, what is happening? A smaller graph, the component size is less than k. In the larger graph, also the component size is less than k. What is going on? And I'm subtracting that probability.
It should be related to the attempts I make to connect the
Graph given you. I've already made this realization of the graph. I'm looking on a smaller graph. My connected component size is less than k. The bigger graph minus of that is what I'm asking. Let me just write the next slide. Because I don't know how to. Don't get it. It's somehow difficult to explain this. The probability that this is the key. E R minus and is given. You have to critically use the coupling just to see this bias. If you can even show this much, that's enough. Don't necessarily have to do it. Isn't equal to that. But is the event clear? What probability are you looking at? Then the smaller graph, the size should be less than k. The bigger graph, it should be greater than k. Okay, so what is the probability of this happening? Okay. Upper bound rate is there. So this question mark is resolved. But we're going further. We want to upper bound this probability. So remember, there is a smaller graph and look at the bigger graph. We're saying no J. Connected component size restricted to this is smaller than K, but restricted to whole thing is greater than K. So what necessarily has to happen? We nail down at least one event for this to be true.
There's at least one edge
Between what and what?
between one vertex from this graph
Yeah.
to outside any other component.
Why are that? The saying is at least has to be this much. This edge exists, because it didn't exist. Then the two graphs are the same in terms of the connected components of J. See, I'm looking at connected component restricted to this graph. That size is less than K. But if I extend it to the full graph, its size is strictly greater than K. So I have to exit somehow.
Okay, yes,
So there has to be at least one edge which allows me to exit.
yes.
Because if there is none, then the two sizes are the identical.
Hmm.
Okay, so now what is the probability? How many such inside outside things are?
There are L vertices outside
Okay.
and
Mhm.
there are N minus N.
But that's too much. Its connected component size is only K. So at most K are in business.
Okay.
And what is the probability? Is P
Okay.
of connection between any two. So it's at most KL times P. Its probability cannot be more than KLP. A is inside, N is outside. B is the probability which I connect. Okay. B remember is lambda over N. So keep doing this over N. Now we are actually done. Now it's all this probability will be put back in the expression. There. This probability is already one. This I am going to keep as it is. What have I done? I've done gone from here to here and looked at this probability minus this probability. But I was really interested in this probability. So I'll subtract this and add this back. So let's call this A. What have I done? Let's call this B. I've done A minus B. Let's call this C. C minus B. That's okay. The A was equal to C.
What are ABs?
A was this probability. B is this probability. They were equal. I'm just subtracting B out from both. And what I have done the next thing is to upper bound this quantity. That is this is equal to less than KL. And what I have here is this times 1 times not A minus B, but A itself. So let me just account for that. If you put the factors back from where, so all the technicalities are over. So there is a square term. This we've already bounded in terms of chi. I only have to worry about these two terms. If you put them together, you get what you want. Eventually, you just get it. So all the technicalities are over. Now it's just a matter of adding them. So then simply get KL, P is lambda over n, and you'll get an extra multiplier, nothing but the chi. Only that you can do. All the technicalities are now just a matter of bookkeeping. So the most important takeaway really is the copy. That's how you compare two graphs with the same connection probability, but two different sets of nodes. So the coupling is the most natural. Start with the smaller graph, add additional edges, add additional vertices, and then allow all the edges to exist. That's all. Okay. So here is the chronology of what we have done. So what we have done is we have controlled the variance. Now, once you have variance control, what is the most obvious thing to control the probabilities? Why do we overcome variances? Which inequality allows us to control probabilities by controlling the variance? That's what we really care about. Markov requires expected values. Exactly. We want to use Chebyshev to get our probability. So what we want to show the probability Pn and to the new order and where new belongs to R and this is the chronology of the result of by controlling the variance. So from our previous result, what we know is the expected value of Z is and order. Remember this, that was shown last time, that the expected value is close to n times the survival probability. So n and n cancels. Okay. And so the event that yeah. Yeah. Is a subset. Why is this true? I want to claim that this is true. So all I've done is replaced NZN or NZN with the expected value. Yes. Miss. The event is that Z deviates from n times IN more than n to the power mu. And here it is, Z deviates from the expected value of Z n to the power mu by 2. Why is this true? When will it be true, Parla? This is n and that is n by 2. As long as the error here is how much this is true. So this is nothing but the error, right? This is the error term. How large or how small should this be for me to allow to do this? Some relationship between K and N to the new.
Yes.
But what is Kn? K log N. While what is N to the new? It's much larger. New is between half and 1. So as long as N is large enough, it's true. Given that Kn is little lower. That's by definition. This is K times log N, and that will always be dominated by N to the power n. So I can always subtract half of it and get that relationship. So how is the error term? The error between the expected value and n xi n is what is being compared. Because here is n xi n, this is expected value. So if they are equal, then this event is the same.
Yes.
I'm saying all that is the difference between them is at most order kn. But kn is little low of n to the new. So I can always say n by 2, at most n by n new by 2. And that's what I've subtracted to get. So the error is no longer more than n to the new by 2. Okay, so now are we in good shape? If you see anytime something like this, random variable minus expectation greater than something, and I have control over the variance of zk. What is the obvious inequality to do? You know, that is why we have actually done this. We have controlled the variance of z because of this particular range. Remember, this is what we really wanted to do. So in my step number 2 or 3, this is my width that I want to show that with high probability this is true. And that is what we have done. But it's not too much more compared to. So the deviation of z greater than k from its mean, or rather, from its mean. Is not good. Then I can say the probability expected value. See, none of this is directly happening. We have this roundabout way. Rather than controlling Zn minus the expected value directly, we looked at expected value in terms of n xi n. And that's how we have actually arrived at them. Because we have control over the expected value in terms of the n times xi n. It's greater than n new is less than 2. Let's call this event A. So that I can mark this. Instead of n to the power mu by 2, this is n to the new. This always be. I just increase the quantity to the left hand side. So this always should be 2. And now how much is this? Chebyshev equality will tell you something. How much is P of A?
There it should be variance of z.
Yes. No, but you can tell me in terms, just in terms of variance. 4n to the minus nu. How large is this now? Quantity in terms of just n. So we bounded in terms of what? In terms of this quantity chi.
Yes.
Right. In terms of this chi. Now, how large is chi less than k? Can you give me a trivial upper bound? most trivial of
A.
k. So just put kn there, you'll get lambda times kn square plus kn times n. That's what I'm going to do. Nothing else. As simple. So it's a weakest bound you can think of. So that will work. And and that kn kn. And for any delta less than 2 mu minus 1, this quantity is at most 10 mu minus because kn square is nothing but kn rather is k log n. You can control all this. And what is lambda? Lambda is
So what is the last step here?
for choosing any delta which is strictly less than 2 nu minus 1. See, lambda is how much in terms of n and p? NP?
Yes.
Okay. What do we get here? Lambda times kn square plus kn. And all of it is dominated by n to the minus delta as long as it's strictly less than 2 nu minus 1. So we got what we want. That the probability that z deviates from n times the success probability of this chain is greater than n to the nu is small. That's all. So essentially, with high probability, you can say it is less than that. That's what it is really. That's how we want to use it. Okay, so now the final step. What we really want to say that. So in terms of these, this is my log n. This is my alpha n. This space ND. That's what we want. Okay, so some notation. Recall I lambda, which was lambda minus 1. Two new things. G of lambda, which is e to the minus lambda. J. This is comma. Okay. So that. Lambda greater than 1. And actually, n would be infinite. It's slightly more general. For any alpha less than xi n, probability that the connected component of V is less than equal to alpha times n and bigger than k is at most p minus kn g log. The proposition here for gamma here is what we are trying to do. Most of the work we have done actually to prove this.
N is k log n, right? There.
So in this particular lemma, k is anything which goes to infinity, then goes to. We'll specialize it when we need it. So k is equal to k log n, which will satisfy the condition that it goes to infinity, then goes to. But this is true for any that goes to. All I need is k goes to. So the lemma is clear, we try to go. Proof is not there. All you have to do is to recall something you did. Remember, we proved something about this Cardo-Shelby process as a function of unexplored and not unexplored, neutral, active, and inactive nodes. And we wrote its growth in terms of how many neutral nodes are becoming active at a particular time. And then there was a surprising result that the new number you're getting is some binomial depending on the previous.
Yes.
So if you remember, let me just state that as an intermediate proposition. We've done this in class. So ST was this process with ST was ST minus 1. Plus XT minus 1. So what was XT? Remember the new, this is exactly the Cardo-Shelby process. And ST was number of active nodes. This was the ST was the number of active nodes. And how was XT evolving? Was binomial with something. It depended on, it was not an independent process, it depends on the previous ones.
N minus 2 plus
N, what is N?
N is what is it?
So N is the total number of vertices. So N minus 3 minus 1. It depended on ST definitely, ST minus 1.
Yes.
It's that you should remember. So let me just put a dot here. But more interestingly, the process ST is equal. I keep going back, I will just take all my time here, but this week the class was n minus 1 comma 1 minus 3 to the power. That was the interesting part. That unconditionally, this is how the process is working. So XT was, if you remember your notation, you'll get everything correctly. It will be a function of ST minus 1. But that's not important. Eventually, we were able to show this that ST process plus a T minus 1 was binomial distributed, and all that interesting thing was happening here. That as T increases, this becomes smaller and smaller.
Minus ST minus 1 plus 1.
This one, whatever that was, it's not
ST minus plus
comma. This is what I want. This is the result I want to recollect, which you already see. So you also know that what is this cardinality equal to as a function of S of T? So this is equal to summation probability PB equal to P. Equal to alpha, sorry, K and alpha. That's correct. And what, so we have seen this, that this is equal to something with respect to S of T. When is it exactly equal to T? When that process is terminated. That is ST equal to 0. Nothing wrong. N, alpha, ST. Now I can use the result which I have about ST being ST plus T minus 1 being distributed like this. What probability I'm interested in? Probability that S of T. So how many boundaries can you give me a bound? As a function of T and T. Or you could use Markov's. S of T equal to 0 means that the binomial is hitting exactly T minus 1. Right. That's not a difficult process. What is the probability that the binomial random variable with these two parameters equal to T minus?
And minus one choose.
He wants nice answer in terms of exponentials. You don't care about exact exponentials. So you can use usual trick of exponentiating and then use the manifolds. Just you eventually use Markov inequality to take part. So before that, you have to just equate this. ST equal to 0 means that the binomial is hitting T minus 1. So that is also less than equal to T minus. And what about complementary one exact ones? So this is equal to T that is binomial dot common dot equal to T minus 1. And this is less than equal to P. Less than T minus 1. I'm just loosening it. Yeah. So I can take this minus 1 out from here and remove that minus 1 also here. That's also fine. By keeping an upper bound. It will be right. This is n minus 1. N minus 1. I want to get rid of minus 1s, let's say. How do I do this? I want to write in T and N. Can I do this? Let me keep a question mark here. Effectively is I'm taking away one slot. You can think of n slot with success probability case. But I'm also taking one from here. And the upper bound. It's not equal. Very good. And now this probability, which is 1 minus p to the t. Oh, yeah. This guy. What can be bounded in terms of exponentials? You've seen this. This quantity. Can you say that it's not greater than 1 minus e to the minus p? The standard. That is what you replace eventually. So currently this dot is nothing but this, but by putting another bond, you can also write this. So this will also be less than p of n comma 1 minus p. This is all like really circus going on, nothing much conceptually happening. All you want to get it in a form which we are happy with. Okay, now at this point I can do an exponential. E to the s times this less than equal to e to the minus s, and by flipping the sign. So what I will is this is probably that e to the minus s. I'm using Markov's. What you look at is C and times that. This is true for any s greater than r. Which is exponential with an s greater than b. That is true for every s. So final bound is yes. Again, don't worry about it. It's just algebra. Nothing really interesting going on. Okay, at this point, there's something interesting going on. And I want to, what do I want to do? As a function of s, minimize its quantity. So that's the tightest bound I can find. So s star does this from the form of n 1 minus so far, nothing really interesting happened. Now there is something to do that.
What is this last line?
Optimizing s star. Oh, it's normally to check something on s star. Or I can just simply plant it back and here is my bound.
Here.
Enough, right? We don't. There is only one star. There are not multiple value of star. So
Yeah, but how do we know that this is
you know.
no minimizing is fine? But in fact, this is positive or non-negative. Because while optimizing, one doesn't really care about s being greater than 0. It's just brute force. Look at this expression. So all you have to ensure is that this is also in fact greater than equal to 0. Yes. Now, so can you give me conditions in which this is in fact true?
The argument is that the bracket should be greater than 1.
Slightly more involved. Slightly more involved than that. This function is kind of special. That's why we gave this the name. This function. You know what is the unique solution of this? This equation. So equal to 1 on alpha. Yeah, so the unique solution for alpha equal to minus the lambda.
What happens if this certified?
So this is where it becomes 1. So equivalently you can think of this as what is the value of alpha from which this is true. So this is an interesting exercise that alpha is nothing but z for that particular lambda. V lambda. This is an exercise where we can actually solve this. So if you plant alpha equal to xi lambda, and that's how so far we have not actually touched xi lambda at all. This is how it actually going to enter the. So this equation g of this equal to 1 only when alpha is actually xi of lambda. Xi is nothing but 1 minus your extinction probability. What you end up getting is here you got this equation is simply showing up there e to the minus. So you should think of t by n as alpha. So again, this is that S star is greater than 0. Leaving these details will take so much of my time. But if you notice that the property we just saw, which is follows. That's really at the heart of it. That this inside thing will equal to t by n only when t by n is equal to alpha. That's what it will do. When you look at any alpha less than psi n, S star will be greater than 0. That's really so. See the book. Or 5 elements. But this is all a pure algebra. Now we are good to go. In the sense, what have we done? So once you plant this S star, it's all this probability will end up being e to the minus t times I g of e bar n comma. But I've defined g before. Just plant this S star. You'll get this. And what is I? G. And J alpha lambda is nothing but IG of alpha lambda. That's what my answer is going to look like. So all I'm going to do is to sum these expressions from Kn going to alpha n. And each of these terms are equal to Kn times e to the minus much e to the minus t j. You can take it all the way to infinity if you want. No problem. That's what you do. The first term is small enough. That's what e to the minus k initial. And everything is multiplied by j. This is what you end up with. Why? Only controlling this process. Taking this whenever it is 0, you already know its distribution, which is not good. Okay, so this is actually, so the corollary to this is to be now I will specialize Kn to capital K log n. So far I've only said Kn goes to infinity, I'm okay. So now what will happen about be that there exists a V. Also, what I've done is only looked at one particular V. Now I have to say for every V, the connected component side is either less than K log n or greater than alpha. So I have to do a union norm essentially over what I have done. So there exists a V with K P of V less than other times. And is at most n times for a particular V test. This is how much from whatever n times e to the minus k n g r divided by. There is no k n here, that's the part. So this is a constant. It's not scaling down with it. N times e to the minus k n is always dominated. That is what. Now we are in the next 2 minutes we'll actually finish everything. So now we have step 1, 2, 3, 4. So just to recap what all we have covered. Okay, so now we have done this. Finally, we have done this, and we are already done this. Now we'll just pass things together. And most importantly, we'll now use. So far, all the control I've got really is on z greater than equal to. So it's very easy to lose this in details. It's very important to keep track of what is the big picture. What events I'm actually controlling. Individually, if you look down closely, they're not very difficult. So let's call it events. Now this is all just putting them together in a format. Let's say event number 1 is. Now k is scalar enough. Minus 10 by that. New is remember as not in the dark such that yeah. These are really the 2 events we have controlled. We have shown both these probabilities are higher. So E is 1 intersection 2. I'll call event E happening when both happen together. What is the probability of the complement? At most, the probability of 1 complement plus 2 complement. And both of them are more small. So E is at most 2 times order n to the minus delta. So this happens to type probability. So E always happens essentially is what. All right. Now what I want to show is that when E happens, Zkn and Cmax are also related and in fact equal. What we have shown so far is that if Kn was greater, Zkn was greater than 1, greater than or equal to 1, then C was at most, Cmax was at most Zkn. That's what we showed. Now, what if it is it possible that it's strictly smaller? What we want to show that when E happens, Cmax fact equal to 0. What we know is then Kn less than equal to then Cmax is less than equal to Zkn. That we know. So when E happens, what about Zk? So E happens means what? E happens implies that Z greater than Kn minus sorry n is equal to n to the new. That's by definition. Right? In E, there are two events, 1 and 2. This is event number 1. So this we know. Now, when E happens, is it possible that Zkn is 0? If this is true, is it possible that Zkn is 0? It's telling you that Zkn is close to n times a constant with a violation of n to the new, where new is strictly between half and 1. So it's not possible that Zkn can become 0. Because otherwise, this quantity is order-wise more than this. So it's not possible. So this implies that Zkn at least greater than 1. So these are the conceptual problems. So that's why I'm stress all these things. Whenever it comes down to theoretic computations, I'm not going to much. But these are conceptual things which you should seriously think about. That if E is happening, this is true. Now, if this is true, it can't be that Zkn is 0. Because otherwise, there is order-wise difference here. That's not possible. How large it is, you can do better estimates. But I'm not going to go there. It's sufficient to look at Zkn greater than equal to 1. Now, if Zkn is greater than equal to 1, we know that this is true. All I have to rule out is strictly less than is not possible. So now look at what happens if C max is strictly less than Zk. What does it mean? All we have to do is to rule this out. And we're done. Because under event E, we say that these two are equal. And I have all the guarantees already for Zk. So the same guarantee is equal for C max. So as soon as you show this, the proof is complete. So what you have to show is that this is not possible when E happens. Over time, but
Max is
you already shown that C max is at most Zk. Now all we have to do is to rule out that it can be strictly less. So the only case remaining is equal. So what does it imply? That if C max is strictly less than Zkn, what does it imply? Does it imply that there are at least two connected components of size Kn? That is sufficient. Because I know there is nothing between K log n to alpha n. So there at least have to be two connected components of size alpha n.
yes.
And then what happens? So this is like a chain you can keep getting. One reduction, second reduction, third reduction, will complete. So this implies that there are two connected components of size greater than equal to Kn. But there is, because of E, there is nothing in between Kn and alpha log n. This implies that there are two connected components of size greater than alpha times n. Okay. Now what is going on? So this implies Z of something is greater than 2 alpha n. What is that something? So does it imply that Z greater than Kn is greater than 2 alpha n? The two connected components, each of size alpha n. So when I'm counting these indicators, all of them will get counted. Right? Okay. So now finally, give me the punchline. If you remember, we already have shown that the keep missing greater than equal to K. N is less than Xi times N 10 to the negative. Already shown this. You choose alpha, whatever alpha we're trying to show is greater than or equal to. Now, does this contradict this information? This will almost true. Alpha's choice is 2 alpha is greater than. So is this possible simultaneously? That this is greater than 2 alpha and this is less than 2 alpha. And this is only a very small fudge factor. So again, otherwise this both together are not possible. So if this is not possible, this is not possible. Because this implies this. Since this is not possible, we end up getting that this in fact is the max. Is equal to. We should make it. And now you have essentially, once you have this, you already proved the bound we wanted for Z itself. What was the bound we wanted? That C max is not too far away from no. In final bound, in terms of the Ardo-Shelby graphs, largest component. What did you want it to be close to? Essentially, n times some constant. So this is exactly it. And it is I times n with a fudge factor of n to the new. So because this is already true, that is already. So we get everything out. I'm not writing it up, but that's what it is. So eventually, what we have succeeded in showing is that if you choose kn to be k log n, these two quantities are equal. And all the inequalities and probabilities are proven for this quantity. Eventually, you have to do something because everything is happening in high probability. You have to make one take one condition probability and finish this. But this is the high level deal.